So my topic is on feebly compact topologies on the semigroup B omega F1. And to introduce this semigroup, I need some additional notions. First of this is bicyclic monoid, CPQ. It's a semigroup with identity 1 generated by two elements, P and Q, subjected only with one condition, PQ is equal to 1. And the semigroup operation on this bicyclic monoid is determined as follows. So we have two elements, q to the power of k, p to the power of l. We multiply it by q to the power of m, p to the power of n, and get q to the power k plus m, and we have shift to the middle elements, middle powers l and m, and we multiply it to the p to the power of l plus n, and also with this shift. And it's easy to see that the bicyclic monoid is isomorphic to the semigroup defined on the such set B omega. It's omega times omega, and we have here following operation. Y1 J2 multiplied by Y2 J2 is equal to Y1 plus Y2 minus minimum J1 Y2, and second coordinate is J1 plus J2 minus minimum between these two coordinates. And we can represent this operation as a system. It's the same, but with respect of these minimums. And now I want to describe the construction which was introduced by Oleg Gutik and Mykola Michalenich in a recent paper. We have some family subsets of omega. By omega, I understand first infinite cardinal, and for any element f of this set and two natural numbers n and m, we put n minus m plus f. It's the set n minus m plus k, where k is in this set f. And subfamily f in p omega is called omega closed if f1 intersect minus n plus f, if f2 is in f for all natural numbers n and f1 f2 in f. And constructor of p omega f is next. Let we have bicyclic monoid represented as b omega, and let we have some omega closed subfamily of p omega, call it f. And the set b omega times f, we define on this set we define semigroup operation similar way as in b omega, but we have here that coordinate, and on the set coordinate we will have j1 minus i2 plus f1 intersect f2 if j1 is less than i2, and in opposite side, opposite case, we will have f1 intersect i2 minus j1 plus f2. In the paper of Gutik and Michalenich is proved that family f is omega closed. If family f is omega closed, then such product with this operation is semigroup. And moreover, if an omega closed family f contains the empty set, then we have ideal in this semigroup. Ideal has such structure. It's all ij and empty set, where ij is in omega. And the main construction has such form. So we have here we have quotient if empty set is in our family f, and if empty set don't belong to the f, we have just the semigroup b omega times f, and such semigroup is called b omega f, and all main of properties were described in this paper too. In particular, there were described all idempotents, green relations, there are criteria of simplicity, B-simplicity, zero simplicity, zero B-simplicity, and so on. And in particular, in this paper is proved that the semigroup B omega is isomorphic to the semigroup omega times omega matrix units. And its criteria, so if and only if F consists of singleton sets and the empty set. So it is interesting to see what will be with this semigroup when F is such form. So let F1 will be the set of all subsets of omega, where these subsets are or singleton or empty set. And it's obvious that F1 is omega closed subfamily of P omega, and B omega F1 is an inverse semigroup with zero. And elements of B omega F1 we will denote by yjk. So here in the third coordinate we will have only singleton or empty set. And the zero, where here is empty set, we will denote zero. Let S be a semigroup with zero and lambda be a cardinal. So in these conditions we can introduce Brandt lambda extension of semigroup S. It is the set lambda times S times lambda with disjoint zero, and operation on this set we have something like this. If these two coordinates is equal, we have at the middle multiplying. If they are not equal, we have zero, and zero multiplied by anyone is zero. Anything is zero, and when we have the semigroup as omega mean, it's a set omega with the operation xy is minimum x and y. We will get Brandt lambda extension of semigroup omega mean. And now it's interesting that we can define a map between our semigroup B omega F1 and lambda extension of semigroup omega mean. The mapping is very simple. We take any element ijk, and after we maps it, we get some new elements with shift to the right. It's I plus k, j plus k. And f from 0 is equal 0 in our Brandt extension. And the proposition says that such mapping is nothing else as isomorphic embedding. So now we can define new semigroup B omega with arrow of omega mean. It's 0 disjoint with ijk with our Brandt extension, and this ijk cannot be 0. And we have a condition that I and j is greater than or equal than k. It's not easy to show that such a semigroup with arrow is inverse subsemigroup of Brandt lambda extension of omega mean, and the semigroup theorem says that semigroup B omega mean with our arrow is isomorphic to B omega F1 by this mapping. And now it's interesting to see some topological properties of this semigroup. Let we have some yj from omega, omega mean ij with arrow. We will denote the elements ikj, where ikj is from our big semigroup B omega with arrow from omega mean. And this next example shows us all compact topologies on the semigroup B omega with arrow. Topology tau IC we defined as follows. All non-zero elements of this semigroup are isolated points, and base at the 0 we define as some neighborhoods where a neighborhood is all semigroup without some finite number of sets of such form. And these sets are finite for any ij in omega, and which implies that this semigroup is the one-point Alexandra compactification of discrete space, b omega with arrow without zero. And also, one of the topological property of this semigroup is that the semigroup B omega with arrow with tau IC topology is Hausdorff compact semitopological semigroup with continuous inversion. And here's some definition, well known for most of us. Topological space said to be compact if each open cover has finite subcover, H closed if each closed space of every Hausdorff topological space in which it contained is closed. Infra H closed if any continuous imagine of X into any first countable Hausdorff space is closed. Feebly compact or so-called lightly compact space if each locally finite open cover of X is finite. D feebly compact if every discrete family of open subsets in X is finite. Pseudo compact if X is Tikhonov and each continuous real valued function on X is bounded. Y compact for some topological space Y if f of X is compact for any continuous map F. And in general case, we have such relations between our compact-like definitions or spaces. But when we have that our B omega with arrow is T1 semitopological semigroup, we can claim that all of these notions are just compactness. So it's a main result of my topic. And here is a list of bibliography, and thank you for your attention. I am glad to answer any of your question.